Okay, so we're going to pick up where we left off in class on example 4. It says, given that sine t equals 5/8 and cosine t equals square root of 39 over 8, use the reciprocal and quotient identities to find the values of the other trig functions for t. All right, so first of all, there is a typo in your book, in your notes that says t equals 5/8. It's supposed to be sine t equals 5/8, which makes a big difference. This time, they are asking you to just use identities to figure this out. Don't use the unit circle. These are not values that would be on your unit circle that we would know as one of our 12 special points. So here we're just going to use our reciprocal and quotient identities, which are basically the functions that are reciprocals of each other, sine and cosecant, cosine and secant, and cotangent and tangent. And then also the quotient identities, one of which is that tangent t is equal to sine t over cosine t. That's just like saying that tangent t is y over x on our unit circle because y is sine t and cosine is x. So this is what we have, and we know that sine is 5/8, so we can just put that right there. And we know that cosine is square root of 39 over 8. And so this is just going to be 5 over the square root of 39. And also notice that both sine and cosine are positive, which means we're in the first quadrant. So we don't need to worry that something is going to be negative, and we're definitely not on one of the axes, so we don't need to worry that anything is going to be undefined. So tangent is 5 over the square root of 39, which I'm going to wait till the end to rationalize that. So then we can go on to cosecant, which is the reciprocal of sine. So we just flip sine upside down, and there's cosecant. Secant is the reciprocal of cosine, and so we flip that upside down. We'll have 8 over square root of 39. And then cotangent is the reciprocal of tangent, and that is going to be square root of 39 over 5. So those are the other 4 trig functions for this t, and we'll go ahead and rationalize the ones that are not rationalized. So this would be 5 square root of 39 over 39, and this will be 8 square root of 39 over 39. So I think there was a typo on this one. Just make sure that it says what it says right here, which is that tangent t is 12/5 for pi less than t less than 3 pi over 2, and then find secant t. All right, so we're talking about now the third quadrant, because remember, here's your plane. 0 is here, this is pi, and this is 3 pi over 2. So the angles between pi and 3 pi over 2 are in here, third quadrant. So be thinking as you go along what things are positive and what things are negative in the third quadrant. Well, the thing that is positive in the third quadrant is tangent, because cosine and sine are both negative. So we just have to remember that when we find secant t, we're finding the reciprocal of cosine, and it will be negative because cosine is negative in the third quadrant. So that's why they're telling us that t is between pi and 3 pi over 2, is to tell us what quadrant we're in, so we'll know what sign we should put on our answer. So if you know the tangent, we're going to use the Pythagorean identities, and I don't have them all memorized. I just memorized this one, sine squared t plus cosine squared t is equal to 1. And then if I need something different, I know that I can either divide this equation by sine squared t or cosine squared t to get the other 2 identities. I have tangent t, and I'm looking for secant t. So I want to get the Pythagorean identity that has tangent and secant in it, or tangent squared and secant squared t in it. The way to get tangent squared is to divide sine squared by cosine squared. So I'm going to divide this whole thing by cosine squared t to get the identity I need. So this is tangent squared t, and this is 1, and this is 1 over cosine squared, which is secant squared t, because secant is the reciprocal of cosine. So now I can just put in the values that they gave me. So they told me that tangent t is 12/5, so this is going to be 12/5 squared plus 1, is equal to 144 over 25, and then 1 is 25 over 25. So that's 169 over 25, and that equals secant squared t. So if I take the square root of that, I'm going to get 13 over 5 is equal to secant t. But I know I'm in the third quadrant where secant is negative, so I need to make this negative. Okay, to express sine in terms of cosine, I'm going to use that same Pythagorean identity, sine squared t plus cosine squared t is equal to 1. And now if I want to express sine in terms of cosine, I just solve this equation for sine. So sine squared t is equal to negative cosine squared t plus 1, and then just going to take the square root on both sides. So sine of t is equal to plus or minus the square root of negative cosine squared t plus 1, or you could write that, probably a better way to write it would be as 1 minus cosine squared t. Okay, so I want to talk about what it means for a function to be periodic, but I think to really understand it, first we should look at what the sine and cosine functions look like, and we're really not supposed to do this until section 4.5, which we're going to do next, but in order to explain what it means for a function to be periodic, sine and cosine are two perfect examples of periodic functions. And a periodic function is just a function that repeats itself over and over again as you go along the x-axis from left to right. So first of all, I want to talk about the sine function. F of x equals sine x. All right, and I'm going to start at the origin. You can see I've got my little graph here where I have my x-axis marked with degrees, and I could have marked that with radians, but I'm marking it with degrees for the moment. And you can see that my y-axis only goes up to 2, because if we're going to talk about the sine and cosine functions, just the very basic sine and cosine functions, we've talked about how the biggest either one of them will get is 1, and the smallest will be -1, because they represent a ratio of a shorter side, or the leg of a right triangle, divided by the hypotenuse. And that's always going to be a fraction where the numerator is less than the denominator, because the legs of a right triangle are always shorter than the hypotenuse. So sine and cosine, their values, their y values, just go between 1 and -1. They never get any bigger or smaller than that. So as we graph f of x equals sine x, we're going to start at 0 degrees, which is the origin. And at 0 degrees, if you look at your unit circle, you can see that y is 0, and that is sine. So at 0 degrees, you have 0 for your y value, so that is 0, 0. Next, if we go up to 90 degrees, that is straight up on your unit circle, 90 degrees, or pi over 2. Then you can see that your y coordinate is 1, so that means that sine of 90 is 1. So as we're graphing sine, we get to 90 degrees on the x-axis, we are now at 1. So the function has increased up to 1. Sine 180 over here, the value of sine there is 0, the y coordinate there. So sine 180 is 0 again. So we're back down to 0 on our graph. And then if we go down to 270, down at the bottom of our unit circle, you can see that y there is -1. So sine of 270 on my xy plane here, the sine of 270 is -1. So I've got the point 270, -1. If I spin all the way around the circle and get back to 360 again, I am back to 0. So here's 360 over here, and my y coordinate is back to 0 again. So you can see that the function it's gone all the way around the circle. It's had every value that it can possibly have from 0 degrees up to 360 degrees. Those are all the values sine can have. Just starting at 0, it climbs, it increases up to 1, and then down to 180, and it goes through there and comes down to -1, and then goes back up again. it has done everything it ever does. The sine function. We've put in every value in for x between 0 and 360. And once you get all the way around the circle, you start over again. You get the same values again and again and again. If I go to negative 90, that is here down at the bottom, because if I go this way now in the negative direction, that's going to be my 90, and we know that at 270 degrees, the y-coordinate is -1, and so sine of negative 90 is -1, so it's back down there. And then when I get up to 180, you can see that the y-coordinate is 0, so sine negative 270 is the same thing as sine 90, and so it's this point right here. And then when I get to negative 360, I'm all the way back around to here, and so sine is 0 again. So I'm back to this spot right here. So as you can see, the sine function just does the same thing over and over again. If you're starting at the origin, it starts at 0, it goes up to 1, it goes down to 0 again, then it goes all the way down to -1, and then it goes back up to 0. And that's everything that function does. And it just keeps doing it. So it did that on the right side of the y-axis, it did it on the left side of the y-axis, it's going to keep on doing it. That same red curve right there is going to get repeated over and over and over again. Now, how often does it get repeated? It gets repeated every 360 degrees. So in other words, the sine of x is equal to the sine of x plus 360. And it's equal to sine x plus 720. And it's equal to sine x plus 3 times around the circle. So this function repeats itself, this whole little red curve, it repeats itself every 360 degrees. So we would say that the period of sine x, is 360 degrees or 2 pi. So that's called the period of that periodic function. The same thing is going to be true for cosine. So I'm going to just quickly graph cosine on here. At 0 degrees, we know that cosine 0 is 1, because if we were looking to find that out on our unit circle, we would just look right here at 0 degrees and we would see that our x-coordinate is 1, and that means that cosine 0 is 1. So for the cosine function, when you put in 0 into that function, you get 1. So the point 0, 1 is on the cosine function graph. That's a red dot right there. When we get to 90 degrees, and I'm just jumping through the quarters, I could put a lot more dots on there, but I'm just going to do this. So when I get up to 90 degrees, my cosine has become 0. I'll have the point 90, 0. All right, the next point I'm going to look at my x-coordinate of 180. If I go to 180 on my unit circle to figure out what cosine 180 is, I'm going to see that the x-coordinate is -1, and that's what the value of cosine 180 is. So on my graph of cosine x at 180 on the x-axis, I will have a value of -1 for my y-coordinate. Now I'm going to go to 270. So 270 is down here at the bottom of my unit circle, and I can see that cosine of 270 is 0. So on my graph of cosine x, when x is 270, y is 0. So I'll put the point 270, 0 on that cosine function. And then when I get back to 360 again, cosine is back to being 1. So the point 360 degrees and 1 is on my cosine graph. So the cosine graph looks like that. It looks exactly like the sine graph, except it's been shifted to the left 90 degrees. And the point right here that we're trying to make, we're not really doing the graphs of sine and cosine yet as far as how do you graph different forms of those graphs. What we're just trying to show is that these graphs are periodic. They do repeat over and over and over again in a pattern. And for cosine, that pattern starts here at 0, it goes down to -1, back up again to 1, and once you get there, it starts doing it again. So the period for cosine is the same as the period for sine. It takes the same amount of x-axis, 360 degrees, for that function to start repeating again. So with cosine, you start in a different place and you end up in a different place. But once you've gone 360 degrees, that function it repeats itself. It does its thing, all the values starting at 1, going down to -1, back up to 1 again, and then it does it again, and then it does it again, and it does it again, and it does that every 360 degrees on my x-axis. So the period for cosine x is 360 or 2 pi, either way. So for cosine and sine, the period of the function is 360 degrees or 2 pi radians. All right, so as I said, function's periodic if f of t plus p is equal to f of t for some constant p. The smallest positive value of p for which f is periodic is called the period of f. The period of tangent and cotangent is pi. For all the other trig functions, the period is 2 pi. All right, so for tangent and cotangent, which we're not going to graph right now, the period is just pi. It only takes half the distance on the x-axis for them to repeat. So for tangent starts over here at 0 degrees. Tangent of 0 degrees is going to be 0 over 1. So tangent, and this is not the example, I'm not doing that yet. So tangent 0 is equal to 0. And then when you get to, say, 45 degrees, tangent 45 is 1. And then when you get up to pi over 2, or 90 degrees, tangent 90 degrees is undefined because you have 1 over 0. So that's undefined. And then you go to 135, which is another 45-degree angle. So tangent of 135 is -1 because you've got square root of 2 over 2 divided by negative square root of 2 over 2. And then once you get to 180 degrees, you're back to 0 again. Tangent 180 is 0. So tangent and cotangent repeat more quickly than sine and cosine. The period for them is just 180 degrees or pi radians. They do all their stuff in that amount of distance on the x-axis. Okay, so given sine pi over 12 equals square root of 6 minus square root of 2 over 4, determine the value of sine 49 pi over 12. So what's the difference between pi over 12 and 49 pi over 12? Well, 49 pi over 12 is just 48 pi over 12 plus another pi over 12. So that is equal to 4 pi plus pi over 12. So because sine is a periodic function with a period of 2 pi, I know that sine pi over 12 is equal to sine pi over 12 plus 2 pi. Because every 2 pi radians, this thing is going to repeat. So at sine pi over 12, it has a certain value, which is square root of 6 minus square root of 2 over 4. So 2 pi radians later, it's going to have that same exact value. And 2 pi later, it will have that value again. So sine pi over 12 is also equal to sine pi over 12 plus 4 pi. And sine pi over 12 plus 6 pi and plus 8 pi. Because every 2 pi, the value repeats. So the sine of pi over 12 plus 4 pi is the same thing as sine pi over 12. It's the same thing. Square root of 6 minus square root of 2 over 4.